Welcome to this lesson on matrix decompositions, where we're going to again be solving AX equals B, and our methods are going to depend on being able to factor the matrix A in different ways. So first we can talk about LU decomposition. And you might remember that when we were doing naive Gaussian elimination, the elimination step itself was kind of expensive. It was order n cubed for an n by n matrix. And then after you get the matrix into the proper form, you solve by back substitution, and that was an order n squared operation. And in many applications, you need to solve the problem AX equals B over and over again for different values of B, right? Maybe M of them, where M is a large number. This can happen in engineering problems, in dynamical systems problems, and other applications. And the thing to note is that the matrix A stays the same each time, and all that's changing is the part way on the right-hand side that's B. And so it would be, well, here dumb is such a strong word, but let's say really inefficient to do Gaussian elimination on the matrix A over and over and over and over again when A is not changing. So the idea is that you somehow store the Gaussian elimination steps and then apply them to B. And so the idea is that we're going to take our matrix A and write it in LU form. L stands for a lower triangular matrix, which means a matrix that has ones on the diagonal, possibly non-zero entries below the diagonal and zeros up here. And then an upper triangular matrix that has 0 entries below the diagonal and non-zero entries above. And I should say this is unit triangular, the lower matrix, because the diagonal entries are 1. And so I'll just give you an example of this. You can take this matrix here and write it in this form. Notice all ones on the diagonal in this lower diagonal matrix, lower triangular matrix, and then here's our upper triangular matrix. And you could carry out the matrix multiplication yourself or using a computer, and you'd find that you recover this matrix A over here. Now, of course, this doesn't tell you how you find out that that's the L and that's the U, but you should be able to verify that it works here. So if you can do that matrix factorization, then your problem AX equals B instead becomes LUX equals B. And really what you do is you solve it in 2 steps. You focus on this part, UX, and you let Y equals UX. And if you do that, then you have the problem LY equals B. Okay, so you solve that for Y. Now that you know Y, you solve Y equals UX to find out what X is. In terms of how you actually perform this LU decomposition, you saw the idea worked out in detail in the book. It basically has to do with storing the steps that you perform during each step of Gaussian elimination. And you can go see those details in the book, or you can ask me to do an example in class. We should talk about the time complexity of doing this, because this is where the value really comes in. So you might remember that Gaussian elimination is of complexity n cubed. It's about 2/3 n cubed operations for an n by n matrix. And so that means that putting A into the LU factorization takes about 2/3 n cubed operations. Then, when you want to do back substitution, there's 2 back substitutions, one to solve Ly equals B, one to solve Ux equals Y, and this takes 2n squared operations for the back substitution. And this means that if you want to solve this whole series of problems for different right-hand sides B, you do 2/3 n cubed to do your initial matrix factorization, and then every time you want to do a back substitution, for your m problems, there's 2m of them, so you have 2m n squared operations. And so in total for this problem, you have this. You have 2/3 n cubed from the matrix factorization plus 2mn squared from the back substitutions. Compare this to what happens if you just do Gaussian elimination over and over again on m problems, right? So you do 2/3 n cubed times m for the Gaussian elimination, And then there's back substitutions as well, which are lower order n squared. But if m is close to n, this is like order n to the fourth, right? This is really big. The point is to notice that here the m multiplies the n cubed, while up here m only multiplies n squared, and so the n cubed term up here is independent of m. I'll point out that R's solve function for solving a linear system uses a version of LU decomposition. We can ask if an LU decomposition exists for all matrices. The answer is no. A few things can go wrong. If there's a zero pivot, your algorithm will fail, and you can see an example of that written out here, right? If you tried to write the matrix 0, 1, 1, 1 in the form of something that's lower unit triangular and something that's upper triangular, you can carry out the matrix multiplication of these two matrices to get something of this form. You'll find that in the upper left entry, you want b to equal 0, but if b equals 0, then this is forced to equal 0 too, and so you can't succeed. In fact, we won't prove this, but we can ask when a square matrix has an LU decomposition, and it turns out to be if and only if the upper left subblocks are non-singular. We should also ask if LU decomposition is unique, and the answer is yes, it is definitely unique. For a matrix A, if it has an LU decomposition, there's only one of them. And so there's a quick way to show this. You can assume that there's two of them. In other words, A is L1U1 and also L2U2. And if you take this equation here and use some matrix inverses, you can rearrange it into this equation here. It's easy to show that both of these matrices are lower unit triangular, and when you multiply them, you get something that's also lower triangular. And you can show that the product of these upper triangular matrices is also upper triangular. And the only way something lower triangular and upper triangular can equal each other is if they match on the diagonal. And since we have ones on the diagonal, it means that their product must be the identity matrix. If the product is the identity matrix, it means L1 equals L2, and it means U1 equals U2. And that shows that the factorization is unique. I'm not going to go through this, but in case you're interested in the pseudocode for writing up the LU decomposition, this can be a handy reference. And we're going to talk now a little bit about numerical error. One problem is, as I mentioned before, sometimes you can have a 0 in the pivoting position here, but let's even suppose that you don't have a 0. Let's suppose that we have something small, and we can demonstrate this unpleasant phenomenon called swamping. So we're going to take the matrix that is almost 0, 1, 1, 1, but instead of a 0, we're going to have a number that's even smaller than machine error. We can try 10 to the minus 20th and put that here. And the LU decomposition turns out to be this. And one thing to notice that we'll come back to later is that the norm of A, so the norm of A, turns out to be much less than the norm of L times the norm of U. Say we take the one norm of these matrices, which is the maximum absolute column sum, then in the, for the matrix A, we get something like it's 2, since 1 plus 1 is bigger than 1 plus epsilon. And then if you look at the L and the U matrices, this absolute column sum is huge because 1 over epsilon is a gigantic number, right? And actually this column sum is huge because 1 minus 1 over epsilon is a really huge negative number that's large in absolute value. So even though A equals LU, the norm of A is way less than the norm of L times the norm of U, and you can file that away for later. So let's see what happens when we do this with machine arithmetic. You can notice that this entry here is problematic. When you store this on a computer, you have 1 minus 1 over 10 to the 20th, and the 1 gets lost in that, and you just end up with minus 1 over 1 to the 20th. You did homework problems like this, right, where you don't have enough precision to keep track of that 1. And then if you take the L matrix and you take that U matrix and you multiply them back, you don't get your original matrix. You get epsilon 1, 1, 0. This entry turns out to be wrong. This problem goes away if we swap rows. So here I've taken the rows of the original matrix A and I've swapped them, and the LU decomposition looks like this here. And if you were to carry out this matrix multiplication on a computer, one thing that would happen is that 1 minus epsilon would turn into 1 because of machine precision. And then you could carry out the matrix multiplication, and here you get a 1, here you get a 1, here you get an epsilon, and here you should get 1 plus epsilon, but the epsilon is lost because of precision. And so we end up with 1, 1, epsilon 1, which is actually what we were supposed to get. So the problem goes away. So the moral is that multipliers should be kept small in Gaussian elimination. In other words, you want to avoid having things like 1 over epsilon, where epsilon is a small number, because that makes 1 over epsilon very large. Now let's talk about something called partial pivoting. The basic idea here is that you don't have to go in order. So there's no reason why AKK, things on the diagonal, have to be the kth pivot. Based on our previous discussion, we'd like to pick the largest magnitude element from candidates that we have, and the way we do this is by doing what we just did, exchanging rows. So one thing you could do is kind of like search through your whole matrix to find the best pivot, and this is called complete pivoting, but it turns out that this is very computationally costly just to find the next pivot. So we don't want to do that. And so the standard method that's used is this thing called partial pivoting, where you just kind of look in a particular column that you're working on in your Gaussian elimination, and you look in that column and just find, given that I have this column, like what's the best element to use for the pivoting here. And it turns out that the overall complexity of that is order n squared. That's on the same order as back substitution, so we're willing to live with that. So the idea is that instead of writing A equals LU like we did before, we write PA equals LU, where this P is something called a permutation matrix that has the effect of exchanging rows in the matrix. So permutation matrices have a single 1 in every row and column, and when you multiply a matrix by P on the left, it exchanges the rows. And so what you do is you choose your kth pivot to be the largest magnitude element from the ones that you're working on in a column. And so you swap the pivot row with row k. And if you write out the steps of doing this in matrix form, it turns out you have like an alternating product of a bunch of lower triangular and permutation matrices. But fortunately, you can show with matrix multiplication properties that you can kind of bring these two permutation matrices together, and you're still left with lower triangular matrices. It changes exactly what they are, but you can still get permutation matrices together and lower triangular matrices together. And if you kind of put this all together, you can arrive at the fact that you can write PA equals LU. So this is useful because all the entries in the final lower triangular matrix are less than 1 in magnitude. That's what we wanted. We didn't want to have to deal with these big multipliers. And it turns out that the complexity is the same as without this pivoting. It's order n cubed overall, and any square matrix can be factorized this way, any square matrix. So when we're solving AX equals B with PA equals LU factorization, here's how we're going to do it. AX equals B, we're going to remember that PA equals LU, so A is P inverse LU, which means that our problem is P inverse LUX equals B, or LUX equals PB. So the first step in solving LUX equals PB is you call this thing Y, and you solve Ly equals PB for Y. And then you have to go back and you have to use that definition and solve ux equals y for x. And the expensive part is still this elimination step, which is n cubed. But then you can use that single factorization over and over and over and over again to solve for different choices of B. Here's some pseudocode for how PA equals LU works. I won't go through all the steps, but this might be a useful reference for you. It's worth us talking about the stability, computational stability of this method. I made a big deal out of an example before where the norm of LU was much bigger than the norm of A, and this caused numerical errors. But when we do this partial pivoting, all the entries in L are small, so the norm of L is always small, and that turns out to save us. So we can define a growth factor, which is defined as the largest of the absolute values of the elements of U divided by the largest of the absolute values of the entries of A. And it turns out that if this growth factor is small, then the norm of U is on the same order of the norm of A, and our algorithm is stable. We don't have these kinds of computational problems that we worried about before. I don't want to make a big deal out of this, but here's when the opposite happens. This is like a really pathological example where I've taken a matrix A and written it as the product of lower unit triangular L and upper triangular U. And it turns out that the growth factor here is on the order of, or is 2 to the n minus 1, which is really horrific. But that's like a pathological case, just to show you the worst thing that can happen. For practical problems, this doesn't really happen usually, and Gaussian elimination, PA equals LU, is considered to be an extremely stable numerical method. I want to spend just a couple minutes reviewing some linear algebra to prepare us for things coming up in the course. So just remember what an eigenvalue is. It goes with an eigenvector, and this eigenpair for a square matrix A satisfies AV equals lambda V. In other words, eigenvectors are the special vectors for a matrix, where when you hit them with the matrix, you get back a vector that's in the same direction, but multiplied by a scalar multiple lambda. So a matrix is diagonalizable if you can write it in the form PDP inverse, where D is this matrix that has eigenvalues on the diagonal and zeros everywhere else. And then what the matrix P is, it has as its columns the eigenvectors of A. And so you can ask, well, when is the matrix diagonalizable? And it turns out that it's whenever you have n linearly independent eigenvectors. If you have them, then you can make this matrix P, and you can do this diagonalization procedure here. There's a related idea called orthogonally diagonalizable, and that's the case if there's a diagonal matrix D and an orthogonal matrix P, such that you can decompose the matrix A this way. What it means for a matrix to be orthogonal is that its transpose is the same as its inverse, which is a really cool thing. And there's this theorem called the spectral theorem for symmetric matrices, and if and only if statements in math are really awesome. So it's that the matrix A is orthogonally diagonalizable only if and only if A is symmetric. Relatedly, a symmetric n by n matrix has n real eigenvalues if you allow for multiplicities of eigenvalues. So no imaginary eigenvalues. The eigenspaces of symmetric n by n matrices are orthogonal, and the dimension of each eigenspace is equal to the multiplicity of its eigenvalue. So if you find an eigenvalue of multiplicity 2, that means it has an eigenspace that's made up of 2 linearly independent vectors. That does not have to happen. In general, there's plenty of matrices where the algebraic multiplicity of the eigenvalue does not have to be the same as the dimension of the eigenspace. So there's this cool thing called the spectral decomposition, where you can write a matrix A as a bunch of linear combinations, and these things represent projections onto orthogonal eigenspaces. That's what you're doing when you write VV transpose, and each one of these is weighted by some weight, which just turns out to be the value of the eigenvalue. So that's kind of cool, and if this seems arcane to you, it's really helpful to just go through a concrete example where you can show this is true. So we talked about symmetric matrices, and now we're going to talk about symmetric positive definite matrices. An n by n real matrix A is positive definite if x transpose AX is greater than 0 for all vectors x, okay? And if it's, instead of having greater than 0, we have greater than equal to 0, we call it positive semi-definite. So in other words, you start with a matrix A, you have to test all non-zero vectors x in this condition here, okay? And you get out some scalar, and if it's always greater than 0, we call it positive semi-definite. And I hope you're thinking, wow, it's really a pain to test every vector, and that's true. And so there's a theorem that says that the symmetric matrix A is positive definite if and only if all of the eigenvalues are strictly positive. There's a kind of related, a corollary that says any principal submatrix of a symmetric positive definite matrix is also symmetric positive definite. In case you don't remember principal submatrix, that's just like if you have a matrix of entries, 1, 2, 3, 4, 5, 6, 7, 8, 9 of them, you pick some element, like maybe this one, and you cross out its row and column, and that leaves you with these 4 entries here. That's a principal submatrix. And why are we even talking about this? Well, symmetric positive definite matrices show up in a lot of applications, and you might see some later in this course. So let's do the example. Here's a 2 by 2 matrix, and we can just take the definition of symmetric positive definite and plug it in for some unknown vector x1 and x2, and you get out this polynomial here, and you can rearrange it to write it as a bunch of things squared, and since it's things squared, you know it's positive definite. You can imagine that this is hard to do for larger matrices. So something related that you can do, like I said, is just find the eigenvalues. So as an exercise, you can take the eigenvalues of all of these matrices and see what happens there. Also, here's an example of a matrix that is symmetric, but not positive definite, right? So symmetric doesn't mean it's positive definite. The matrix is symmetric, but here's an example of a vector where when you plug it in, you get a negative number. All right, thanks for listening.